Would anybody like to buy a used French rifle? It's never been fired and it's only been dropped once. The French have something of a reputation for cowardice, owing to their lackluster performance in World War I and II. We'll leave it to the historians to decide whether this reputation is well deserved. Our topic today is more of an American phenomenon. American colleges and universities, including the service academies, are not producing enough graduates in science and engineering majors for America's economic and military strength to continue into the foreseeable future. This phenomenon is rather simple to understand. It is attributable to the fact that lots of aspiring science and engineering majors attempt to succeed in the discipline while maintaining their high school habits of preparation. When they get to the first course that really requires completing every assigned homework problem for success on the graded events, rather than persevere, they give in to the temptation to change their major to an easier subject. Would anybody like to buy a used Calculus 3 book? It isn't very well worn, and it's only been dropped once. Hi, I'm Dr. Courtney with the Quantitative Reasoning Center. Today we're having a look at 14.4, number 24, and we've changed some of the numbers just a little bit, so be careful as you're working this at home to work with this with the same numbers as the book. And the problem asks us to find a linear approximation centered at, so we want to find the linear approximation centered at negative 15 degrees C and 50 kilometers per hour, and use it to approximate the wind chill at negative 18 degrees C and 55 kilometers per hour. So basically the wind chill function here is a function of the temperature and the wind. In other words, the idea behind wind chill is that the perceived temperature depends both on the actual ambient temperature as well as the velocity of the wind. So this is the perceived temperature, the actual temperature, and the velocity of the wind. And we need to use the table that we're given to generate a linear approximation. So the big idea is to use the table to generate a linear approximation, and we'll call our linear approximation L of t and v. Alright, so one of the important things as we develop the problem is to think about this table, and we're actually going to use the table itself as our picture because there's part of the table that's of interest and then there's some extra information in the table that we really don't need. So we're going to focus on the part of the table that we really need, and that's the part of the table kind of centered around a temperature of negative 15 degrees and a wind speed of 50 kilometers per hour. So if we have the wind speed in across the top and the temperature down, we need to focus on the 3 rows and the 3 columns of the table that are really important and centered around 50, and this is kilometers per hour, and negative 15 degrees C. And the reason that we need a lot of the table, or this subset of the table, is because just like when you were using tables in Calculus 1 to estimate derivatives, you would often end up using the table entry on either side of the point of interest. We need the table entries on either side of the point of interest, both in terms of the wind speed as well as in terms of the temperature. So the one right in the middle, negative 29, is actually the one that we don't end up using directly, but we end up using the ones around it. Negative 22, negative 35, negative 27, and negative 30, because, and we also need to know what the wind speeds are. This is 40, this is 60, all in kilometers per hour, and this is negative 10, and this is negative 20. And so this is going to be important in our development. So as we make our plan, the first thing that we're going to do is we're going to express the formula for our linear approximation, which we're calling L of t and v, in terms of the derivatives. And because this is Calculus 3, these are partial derivatives in view at this point. And then we use the table to estimate the partial derivatives. And you will see that this is similar to using a table to estimate partial derivatives in one-dimensional calculus, although now we've got two variables and we need to handle the little bit of extra complexity that involves. And then it's simply plugging in the numbers into the formula, evaluating, and simplifying. Alright, so as we execute or evaluate, what's this formula look like? Well, let's first take a step back and think about how the linear approximation worked in one-dimensional calculus. In one-dimensional calculus, is if you have some function of x and then you develop a linear approximation, it's equal to that function evaluated at the point of interest, or the center of action, however you want to think about it, plus the first derivative. And let's go ahead and let's use the Leibniz notation for derivatives here. The first derivative evaluated at that center point times the difference between the variable and the center. And we want to recall as well that this formula originates in the point slope form of a line. Y minus y naught is equal to m times x minus x naught. If you're given the slope of a line and a point x naught, y naught that the line goes through, and if you want to make an exact analogy, y would be y naught plus m times x minus x naught. And what does all this mean? Well, it means the output of a function can be approximated by the output of a point close by plus the slope of the line at that point times how far did you move away from the point of interest where you generated the output of the function. Alright, so let's go ahead, and now that we've reminded ourselves how the linear approximation works in one dimension, let's go ahead and develop the formula L of t and v. Well, that's going to be equal to, it's going to be equal to the value of the function at the center, at the point of interest. So it's going to be equal to f of t naught v naught plus the partial derivative of f with respect to t evaluated at t naught v naught times t minus t naught. And what this accounts for is this accounts for the slope in the temperature direction. How fast is the function changing when the temperature changes by 1 degree, times how far you moved in temperature. But now since we're in 2 dimensions, and let's go ahead, we don't have quite enough space to finish it there. So plus partial f partial v, evaluated at that point of interest, times v minus v naught. So this part here is analogous to the one-dimensional situation, and this accounts for the fact that we have 2 independent variables. So this tells us which derivatives we need to estimate, namely the partial of the function with respect to t around the center point and the partial of f with respect to v around the center point. And we kind of took some care at the beginning to only recopy the part of the table that we were going to need. All right, well, let's make a little room back over here so we can fit stuff in, and let's set ourselves to computing these derivatives. So we want partial f, partial t, and we're not really computing the derivatives exactly, we're estimating them at t naught, v naught, and what this is it's the change in the output divided by the change in the input centered at this point, and it's with respect to the variable t. So the change in the output we can think of as the difference between these two numbers. So this is negative 35 minus negative 22, and you divide by the change in the input, which is negative 20 minus negative 10. So this works out to be the negative, and the negative is the positive. So this is negative 13 because you're adding 22 to negative 35, and this is negative 20 plus 10, or negative 10. So this is 1.3, and it's the units of the output, which are degrees C, divided by the units of the input, which are also degrees C. So what this is telling you is that when the actual ambient temperature increases by 1 degree, the perceived temperature increases by 1.3 degrees. All right, and that's true when you're close to this point, when the temperature is negative 15 and the wind speed is 50 kilometers per hour. All right, let's estimate the other derivative that we need. Oops, and this is the one with respect to the wind speed. So the points of interest are this one and this one. So we have negative 30 minus negative 27 divided by 60 minus 40. So this derivative works out to be, well, the negative and the negative give you a positive. So this is negative 3 divided by 20. So you can think about this as 0.15, and it's negative. And the units are the units of the output, degrees C, divided by kilometers per hour. All right, so now we can plug into the formula here. Our linear approximation is the value of the function at the center plus the value of the derivative with respect to t, which is 1.3, and then t minus t naught, so this would be t minus, and t naught is negative 15, and the negative is a positive, plus the derivative with respect to v, and that's negative, times v minus v naught, and v naught is 50, so this would be v minus 50. So taking care with the units, this expression here is the linear approximation. So let's go ahead and assess at this point, before we do the last part, to use the linear approximation to estimate the wind chill for certain values. Let's evaluate this first. Does this make sense? Well, does it make sense that close to this point the value of the wind chill is close to what the wind chill is at that point? Well, sure, that makes sense. Does it make sense that as the temperature increases with respect to the center point, the perceived temperature increases by almost the same amount? For every degree in temperature increase, the perceived temperature increases 1.3 degrees. Yeah, that kind of makes sense. And does it make sense that as the wind speed increases, the perceived temperature decreases a little bit? Yeah, that makes sense. I've stood outside in the wind on a cold day. It's colder when the wind's blowing. Alright, so that kind of makes sense. So now we want to use this to evaluate. We want to basically compute the linear approximation at the temperature of 18, at negative 18 degrees, and the wind speed at 55. Alright, so that's just plugging in negative 18 here, plugging in 55 there. So it's going to be negative 29 plus, and negative 18 plus 15 is going to be negative 3. And then minus 0.15, and 55 minus 50 is going to be 5. So you can punch these numbers into your calculator, and let's once again just think about whether or not it makes sense. The fact that the actual temperature is a little colder by 3 degrees is going to reduce the perceived temperature by about 3.9 degrees. And the fact that the wind is blowing 5 kilometers per hour more is going to reduce it by an additional 0.75 degrees with regard to the wind chill.